Hello, this is another WJEC Unit 2 A-Level Physics question. This time it's from January 2010. It's question number 4, and it's about the photoelectric effect. The first part of the question gives us Einstein's photoelectric equation, and we're asked what does a quantity HF represent. And notice it says a quantity of energy, so writing down something like Planck's constant times frequency gets you nothing. We need to remember that HF is the energy of a photon. Next, the student mistakenly thinks that the minus sign should be a plus sign. We've got to explain in terms of electrons and photons why the equation must be correct as written above. Well, HF, as we've already said, is the energy of the photon. The letter phi in the equation is the work function. And if we define that, it's the minimum energy needed to remove an electron from the surface of a metal. So what's going to happen here is that the energy of the photon will first of all overcome this work function to allow the electron to escape, and then any energy that's left over will be available to become kinetic energy of that emitted electron. So let's say something like EK max is the energy left over after overcoming the work function. And it's going to be the kinetic energy of the electrons that have escaped. So basically the idea is that the energy of the photon first of all overcomes the work function, allows the electron to escape from the surface of the metal, and whatever is left over becomes that maximum kinetic energy of the electron. For the next part of the question, you're given some data and the points have to be plotted. So I've already plotted that data and drawn a line of best fit through that data. The second line, you'll see the reason behind that later on in the question. When you're plotting, be very careful. Try to plot the points as carefully as you can. They generally need to be within half of a small square of where they should be on the graph there. And it's worth remembering here that the intercept on the y-axis is going to be the work function of the material. So extend the graph, extrapolate it until it does cut the y-axis. So the next part of the question asks us to either using data or the graph to determine the work function for the sodium, and as mentioned earlier, the quickest way of doing that is just to look at the intercept on the y-axis, and you'll see that that's approximately 3.8, but you mustn't forget that there's a 10 to the minus 19 multiplying factor as well. Now next we're asked to determine the Planck constant. If we've learnt our work properly, we should know that the Planck constant h is actually the gradient of the line of best fit that we've drawn. So always remember that when we find a gradient, try to use a large triangle. So I've added a dotted line across the bottom of the graph showing that our triangle that we're using is basically the entire length of the graph there. And we're looking at going from minus 3.8 up to 4 times 10 to the minus 19. So that gives us our delta y is 7.8 times 10 to the minus 19 joules. And on the bottom of the graph, we're finishing just very slightly before the 12 times 10 to the 14. We're actually finishing at 11.8 times 10 to the 14. Putting those figures into a calculator should give us an answer of roughly 6.63 times 10 to the minus 34. and these figures actually give us 6.61 times 10 to the minus 34. Units is joule seconds, so our answer is pretty good, it's pretty close to the value that we expect. That should be an equal sign at the start. The final part of the question was to draw a line labelled 3 on the grid, which would be obtained if a metal with a lower work function were used in the experiment. So that's this line here, so if I label it as 3, basically the gradient must still be the same, so it must be parallel to the original line, and if it's got a lower work function it needs to intercept at a less negative value on the y-axis. So thank you very much for listening, and please like and subscribe.